Hi everyone. Nail diseases are quite common. In general, around 1 out of 4 people get a nail disease at some point, and if you have it, it can be expensive to see a specialist to get treatment. But if you have some kind of insurance, you still might have to wait for a long time to get an appointment. Actually, there's some data from Berlin. It takes a median of 76 days if you have like a state insurance to get an appointment. And that's the median because there are many outliers. For some people, it takes several months. If you have a private insurance, it's 22 days. It's a bit better. Yes, so the idea of our project was basically to see if computer vision can do this task. To detect and classify these diseases. And the second part is actually to predict the severity of diseases. Okay, so we focused on these 5 different classes: healthy nail, nail fungus, nail dystrophy, onycholysis, like the lifting of nail, and melanonychia. Sorry, it's quite hard. We used a large database from Korea with more than 50,000 nail images. And actually, there's a paper that already looked at 2 of these disease images, onychomycosis and nail dystrophy. And they found that a model can distinguish these quite well, actually. They used an ensemble model of VGG19 and ResNet 152. And these are area under the curve values in RC graphs. So this actually works quite well already. But still, the first thing we did was try to come up with our own model, because this paper is from 2018, and we thought maybe we can even get better results or similar results. So this was the first step. We tried a bunch of architectures. In the end, decided to go for ResNet 152 and EfficientNet 5 as an ensemble. And we had 6 classes of diseases that we trained on. It's back. Another thing to note is that we used strong image augmentation. Here's an example. So this was cut out and mix up. So small parts of the image are cut out. And there's also an overlay of 2 images, basically. This allowed us to train for a long time and potentially get a good performance in the end. So here you see the results we got. Actually, in 3 out of 4 test sets, we were able to get a better score. So this is quite cool already, and it's comparable because we used an ensemble model just like in the paper, and also the training set was pretty much the same, or actually exactly the same. However, one should also note that these results are not very reliable because the test sets are quite small, and this is also only for these 2 types of diseases. So healthy nails were not included in there. And also we wanted to see if these results transfer to Europe, because this was only a Korean data set. So that's why we decided to come up with a test set of European nails from 5 different classes, and we scraped these images from Google using 10 European languages. And we cropped the nails from the images using a YOLOv5 segmentation model. So in the end, we just had these small crops, but we had to exclude many images because they were of quite low quality, or duplicates, or images with more than 1 disease, which made class assignment unclear. So in the end, we came up with this distribution of cases on the right. And the model actually worked really well for distinguishing healthy nails and nails with disease. You can see here the F1 score is quite high. It didn't work that well for distinguishing between different disease types, but it worked best for melanonychia with a very good F1 score and particularly high precision. We also got decent recall for these 2 other diseases, but a quite bad recall for onycholysis disease, which kind of made sense for us because many of these images look like normal nails to us. I mean, we're not doctors, but it looks like can be easily confused, and actually that's what we also found in the end in the confusion matrix, that the model has most problems distinguishing healthy nails from these onycholysis type of nails. Another thing we looked at was gradient-weighted class activation mapping, which is basically a technique that allows you to see where the model is focusing in making these predictions, so where on the image. And in this case, the ground truth is melanonychia, and the prediction is the same, so it's correct. And you see that the model is focusing on the nail in these images. But it's not particularly focusing on this dark stripe, which is characteristic for this type of disease. So yeah, but still the whole nail seems to be focused. And if it's doing a wrong prediction on the right, it's still focusing on the nail. This is also true for this other type of disease, onychomycosis. It's focusing on the nail, but surprisingly, it's not focusing on the nail when it's predicting nail dystrophy. This was also the case when ground truth was nail dystrophy. It always focuses the parts outside of the nail somehow. And we observed the same sort of pattern for onycholysis disease. These two diseases have the lowest F1 scores, but it's hard to tell why this is the case without conducting some more experiments on this. All right, so the second part of our project was to predict the severity of disease. In medicine, there's this severity score for a nail fungus, and it's made up of 3 components. The first one is the area affected of the nail in percent, and the second one is the proximity of the disease to the lunula, which is like the area where the nail is growing. So it's bad if it's closer to the lunula. Yeah, and there's a third component, but we actually focused on only the first one, the percent affected. And to approach this, we segmented a bunch of images to first get a segmentation of the nail as a whole. So we collected these images and annotated them, and we then split them into train and validation set, and used a YOLO v5 segmentation model, which is pre-trained on the COCO database with 80 different classes. We fine-tuned this model, and as you can see, it works really well. It's basically performing almost perfectly between these predictions and ground truth. There's not much of a difference. All right, so the next step was to segment the area that's affected by fungus. And for this, we again annotated a bunch of images and split them so that we had the same validation set. Again, used the YOLO segmentation model. And the performance was also quite good, actually. It's not as good as for the nail because it's a much more difficult task to segment the affected area than to find the nail. But still, it was really, really quite good for us as a first attempt. Okay, so now we can compare the ground truth proportion of the nail affected to the predicted proportion affected on an image-to-image level. So this is what we got out of this. The mean average error is around 10%. So this means that on average, we are off by 10% from the ground truth proportion affected, which is not bad. And another thing one can look at is the dice coefficient, which is used to compare pixel-wise agreement of segmentation masks. This is basically the overlap of the 2 masks, 2 times the overlap divided by the sum of the 2 masks. And the dice score was around 0.8, which is also quite high and indicates a high pixel-wise agreement of the masks. Okay, so for future work, it would be interesting to look at the second component of the severity index, the proximity of the disease. So one could train a detection model on the lunular part of the nail, and then use key point detection for finding the edge of the nail, the central edge, and also the beginning of the nail, which is marked here in blue axis. And then you can sort of draw in these areas and calculate how close the disease is to the to this lunular part. Yeah. So in the future, it would also be good to have medical professionals look at these labels and revise them maybe and to get a even more better result in the end. And with some more work, we could come up with an application where people can upload their images, and then it can be detected, and they get a value for how severe this is as well. To conclude, artificial intelligence is already very good at detecting and classifying nail diseases, and this also applies to European nails. And secondly, for the first time, we have shown that AI can also have high potential for severity prediction. Okay, thank you, everyone. Also, thanks to Markus Hinsche for being our mentor, and also thanks to everyone else at DSR.